Today, we're diving into one of the most mind-bending truths in all of physics, a truth that will completely change how you think about time, memory, and reality itself. We're exploring why the past isn't gone, why every moment you've ever lived still exists right now, and how Richard Feynman, one of the greatest physicists who ever lived, proved that time isn't what you think it is. This is going to challenge everything you believe about the nature of existence. But before we begin this incredible journey, if you want to keep exploring the deepest mysteries of physics with me, hit that subscribe button right now for Discover Physics. Don't miss future videos where we uncover the hidden truths about reality. And if this video blows your mind, give it a like to help more curious minds discover these ideas. Now, let's dive into why the past never actually left. The past has vanished. Everybody understands this fundamental fact. Those events occurred. They concluded. They're finished and behind us now. We retain memories of them, certainly, but they no longer exist in any real sense. Correct? Incorrect. Absolutely, fundamentally incorrect. And Richard Feynman can demonstrate exactly why the past hasn't disappeared anywhere. It never departed at all. It remains here right now at this very moment, intricately woven into the fabric of absolutely everything you observe and physically touch. And once you genuinely comprehend why this is true, you will never contemplate time in the same way again. Allow me to illustrate what I mean by this. Right now, at this instant, you're situated somewhere reading these words, existing in what you label as the present moment. You conceive of now as a singular point in time, a razor-sharp edge dividing past from future. The past sits behind you, completed, finalized. The future hasn't manifested yet. And you find yourself trapped in this incredibly tiny sliver called quote, _1_. But here's the fundamental thing Feynman grasped completely. That mental picture is mistaken, entirely mistaken. Time doesn't function that way at all. The present moment isn't actually a point. The past hasn't disappeared, and the future isn't patiently waiting to happen. Everything is far more connected, more intertwined, more simultaneous than you have ever imagined possible. Now, Feynman possessed this extraordinary gift for taking the most mind-bending ideas in physics and making them feel obvious, almost simple. And when it came to understanding time, he perceived something that most people completely miss. He saw that when we discuss the past being gone, we're making an assumption, a rather large assumption. We're assuming that time flows forward, that it moves like a river current, carrying us inexorably from past toward future. That moments happen and then dissolve, replaced by new moments. We think of time like turning pages in a book where you're always on the current page, and the previous pages, well, they're behind you now. You can remember their content, but they don't exist in the same concrete way the current page exists. But what if that's not how it actually works? Here's what Feynman would explain to you. In physics, in the actual mathematical description of reality itself, time doesn't flow. It just exists. All of it, past, present, future, they're all equally real, equally existing. They're all integral parts of the structure of the universe, similar to different locations in space. Think about it from this perspective. You don't think Los Angeles ceases existing when you happen to be in New York. You don't think New York disappears completely when you travel to Los Angeles. They're both genuine places. They both exist simultaneously at the same moment. You just cannot be physically present in both at once. Time, according to rigorous physics, works the exact same way. Yesterday is a location in time. Tomorrow is a location in time. They're both real. They both exist. You just cannot be present in both at once. You're currently located at today, but that doesn't make yesterday any less real than Los Angeles is when you're standing in New York. Now, I know what you're thinking at this moment. That sounds completely crazy. You can physically go to Los Angeles. You can purchase a plane ticket and fly there, but you cannot go to yesterday. You cannot travel backward to the past. So how can they possibly be the same? And that's a legitimate question that deserves an answer. But here's the crucial thing to understand. The reason you cannot travel to yesterday has absolutely nothing to do with whether yesterday actually exists. It has everything to do with the fundamental structure of spacetime and the laws governing physics. There are strict restrictions on how we can move through time, just as there are restrictions on how we can move through space. You cannot travel faster than light through space. That's an inviolable law of physics. But that doesn't mean the places beyond your light cone don't exist somewhere. Similarly, you cannot move backward through time under normal circumstances. But that doesn't mean the past doesn't exist somewhere. Feynman understood this at a profoundly deep level. He worked extensively with something called the path integral formulation of quantum mechanics. And in that mathematical formulation, particles don't just take one single path through spacetime. They take all possible paths, every conceivable path simultaneously. A particle traveling from point A to point B doesn't just travel in a simple straight line. It explores every possible route, including ones that loop backward in time, ones that zigzag wildly through space, ones that take elaborate detours through every corner of the universe. And all of those paths contribute mathematically to the final observable result. All of them are real in a meaningful sense. Now, the paths that go backward in time, the ones that violate our normal intuitive sense of causality, they mostly cancel out mathematically when you add them all up. They're present in the mathematics, but they interfere with each other and don't contribute much to what we actually observe. But they're not forbidden by the laws. They're part of the mathematics. They're part of how the universe actually works at the deepest quantum level. And this reveals something profoundly important. The distinction between past and future, the arrow of time that feels so obvious and natural to us. It's not fundamental to reality. It's not built into the basic laws of physics at all. The fundamental equations work identically, whether time runs forward or backward. If you filmed the interactions of particles and played the film in reverse, you couldn't tell the difference. The laws simply don't care about direction. So where does our powerful sense of time's arrow actually come from? Why does the past feel fundamentally different from the future? Why do we remember yesterday but not tomorrow? Feynman knew the answer perfectly well. It comes from entropy, from the second law of thermodynamics, from the fact that disorder increases over time in closed systems. But that's a statistical law, not a fundamental one. It's about probabilities and large numbers of particles behaving collectively, not about the deep structure of time itself. Let me explain what that actually means. Imagine you have a box filled with gas molecules. At the start, all the molecules are crowded in one corner of the box. That's a low entropy state representing a high degree of order. Now, you release the molecules and let them spread out freely. They rapidly fill the entire box. That's a high entropy state, much more disorder. And here's the key insight. This process is vastly more likely to happen than the reverse process. It's incredibly unlikely that all the molecules would spontaneously gather back in one corner by chance. Not impossible theoretically, just fantastically improbable. So when we watch this system evolve, we see entropy increasing steadily. We see order turning into disorder, and we declare time is moving forward. But notice something crucial. The molecules themselves don't know anything about time's arrow. Each collision, each individual interaction between molecules could just as easily run backward in time. The laws governing those collisions are perfectly time-symmetric. The arrow of time emerges purely from statistics, from the fact that there are vastly more disordered states than ordered states. So systems naturally evolve toward disorder. That's it. That's the complete explanation of where our sense of past and future comes from. Not from time itself, but from entropy. Now, here's where it becomes really interesting and important. Because of this, because the arrow of time is statistical and not fundamental, there's a genuine sense in which all moments in time are equally real. The past hasn't gone anywhere at all. It's still a legitimate part of spacetime, still a valid location in the four-dimensional structure of the universe. When physicists write down the equations describing the universe, they include all of time, past, present, future. It's all there in the mathematics. It's all part of the complete solution. The universe, from this view, is a four-dimensional object. 3 dimensions of space, 1 dimension of time. And just like every point in space is part of the object, every moment in time is part of the object. The Big Bang is part of it. The moment you were born is part of it. This moment right now is part of it. The heat death of the universe billions of years from now is part of it. All of it exists. All of it is real. We just experience it sequentially because of how our consciousness works, because of how memory and causality function in a universe with steadily increasing entropy. Feynman had this remarkable way of making you see that our everyday intuitions about time are parochial, limited. We think time flows because we directly experience it flowing. We think the past is gone because we cannot go back to it. But those are facts about us, about our limited perspective, about the constraints of our consciousness and memory. They're not facts about time itself. It's like a bug crawling on a ball from another example. The bug thinks its entire universe is two-dimensional because it cannot perceive the third dimension. We think time flows because we cannot perceive all of time at once. But the flow is an illusion created by our particular way of experiencing reality. Now, let me show you something that'll really bend your mind significantly. You know how we think of ourselves as moving through time. We imagine we're traveling forward exactly 1 second per second from past toward future. But there's another way to think about it. What if you're not moving through time at all? What if you exist at all moments simultaneously, and consciousness is just the experience of different time slices of that four-dimensional object that is you? Let me explain this carefully. Imagine your entire life as a long worm-like object stretching through space-time. One end is your birth. The other end is your death. And in between, every moment you've ever experienced, every moment you will ever experience, they're all part of this extended object. This four-dimensional worm is the real you, the complete you. Now, at each moment, you're only conscious of a thin three-dimensional slice of this worm. You experience one moment at a time, sequentially. But that's just your limited perspective. From outside time, from a God's eye view, all of you exists at once. You at age 5, you right now, you at age 90, all equally real, all equally part of the structure. This is called the block universe view, and it's a natural consequence of Einstein's special relativity, which Feynman knew intimately and profoundly. In special relativity, there's no universal quote 2 that everyone agrees on. Different observers moving at different speeds will disagree about which events are simultaneous. What I call quote 3, you might call the past or the future if we're moving relative to each other at high speed. And if there's no universal quote 4, if simultaneity is relative to the observer, then the present moment isn't special. It's just a particular slice through space-time that you happen to be experiencing right now. And that means the past and future are just as real as the present. They're other slices through the same space-time, okay? Now watch this, because this is where Feynman's genius really shines brilliantly. He didn't just accept this abstract picture philosophically. He showed how it actually works in practice, how it explains real phenomena. Take antiparticles, for example. An antiparticle is like a normal particle, but with opposite charge. The antiparticle of an electron is a positron. Same mass, opposite charge. Now, Feynman had this incredible insight that changed everything. He realized that you can think of an antiparticle as a regular particle moving backward in time. I'm not kidding or exaggerating. This is actual physics, not science fiction. When a positron moves forward through time, it looks exactly like an electron moving backward through time. The mathematics is identical. And Feynman used this idea to develop his famous Feynman diagrams, which are pictures showing how particles interact. In these diagrams, time is usually shown going upward on the page. A particle moving up is going forward in time. A particle moving down is going backward in time, which we interpret as an antiparticle moving forward in time. Now, here's the beautiful part. This isn't just a mathematical trick or clever notation. It's revealing something deep about the nature of time and particles. It's showing that the distinction between past and future, between particle and antiparticle, is more subtle than we thought. It's showing that time-reversed processes are just as valid as time-forward processes. And it's showing that the past is still there, still part of the structure, still contributing to the present. Because when you calculate what happens in a particle interaction using Feynman's methods, you're summing over all possible paths, including the ones that loop backward in time. Those backward in time paths correspond to antiparticles, and they're absolutely essential to getting the right answer. Without them, the calculations don't work. The past, in this sense, is actively participating in the present moment.